Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
That's us. Yay. Hello, I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and bud to the universe.
Yes, you are. And I'm Corinne Caputo, a writer, a comedian, although, light on the comedian these days.
Corinne, you're funny.
Thank you.
Yeah.
Sometimes I'm like, can you use that if you've written funny things but don't perform on the stage anymore?
Yeah, absolutely. I think so. So as a science communicator, I've been doing a lot more speaking than writing lately. Mm-hmm. But there are so many science communicators who are just writers. And, I still call myself a writer.
Yeah, I get to pick.
Yeah, it's like a king or queen of Narnia situation.
Yes.
Once you do this, you're always this.
I love that. And that's me then. And I'm also a friend to the universe. And, just this weekend, somebody said to me that they are afraid of space. And I was like, boy, do I have the podcast for you.
Did it feel like a weird self-plug? Do you ever feel weird about promoting your own work?
So often.
All the time.
Like, I'm always, proud of the work that I'm doing. I think I'm lucky in that I'm not really doing stuff ever that I don't like. But it's still, it feels kind of braggy, and, that's not a thing I've ever gotten super comfortable with. Yes. The most challenging part of, this work to me is playing, the manager or the agent for yourself. Mm-hmm. So I'm always I kind of have to, pretend that it's not me for a second and be like, how would I talk about myself if I was a client?
Oh, that's smart. That's a smart way to think of it. I just don't. I just avoid it.
Yeah.
It helps a little bit that my friends in college realized pretty quickly that the surest fire way to embarrass me was to give me compliments and brag about me, because I hate it. It's one of the only things that will make me blush. So they do it.
Yeah, of course.
So I don't have to.
Well, it's so weird. I hate doing it, but when I took that love language quiz, when everyone was, words of affirmation was my love language.
It's a good one.
I'm a Leo.
I'm a touch person.
A lot of people are. So's my husband Eli, and I'm just couldn't be me. We speak different love languages.
Right. It's so important. Well, that's that on love languages. And our anxiety around self-promotion. Today, we're not talking about that. That's not what this episode is about. Surprise, surprise.
But if you want to recommend us to your friends, do it.
Please do, because we're not going to.
Yeah.
So today, we are recording in some batting cages.
Yeah, we are.
I do not like baseball. I am so bad at hitting a ball with a bat. I think that my fine motor skills just aren't that refined.
I totally get it.
Give me a rugby ball or a basketball. I'm good, but I guess I just...
You need a larger object.
I need to work with bigger balls, Corinne. That's what we're saying.
I get it. I have never been good at baseball either. I was on a softball team for years in New York.
Ooh.
It was a recreational softball league. It was a co-ed league, so you need a minimum number of women. They were really specific about co-ed rules, because I think what had happened in the past is it's just male teams would join, and it wouldn't be the vibe they wanted.
That makes sense.
So I was never very good, but I created a system for home runs, which is if you get to first base, it's a quarter home run, and if you get to second base, it's a half home run, and so on. And I think we should use that all the time in baseball, because it makes you feel really good.
They call that just a run, Corinne.
I know, but if you say it's a half home run, it's oh my God, you got a half home run.
You're so half impressive.
Yeah, exactly.
So neither one of us super into baseball, but I thought that for what we're talking about today, it'd be helpful to be around batting cages, because I think that I can use it to help demonstrate a point I'm going to make later.
I love this.
Mm-hmm. So today we are talking about the amazingly useful phenomenon in science in general and in astronomy more specifically of redshift and its counterpart, blue shift.
Ooh, I feel like I have heard of this, but I don't know if I have. I think I'm just confusing it with The Matrix.
Oh, with the red pill, blue pill thing?
Yep. Yep.
Mm-hmm, mm-hmm. I mean, I think a lot of people have heard of redshift and blue shift in the context of the Doppler effect.
Yes.
Do you remember hearing about that in, physics class?
Exactly. I remember that in physics. I had a physics teacher I loved in high school, and that was a fun day.
Good. This is different from the person who told you the moon landing was fake.
Different. Oh my gosh. That was my middle school teacher.
Okay.
High school was a lot better.
Great. Good. You're stepping up in the world.
Yeah.
So redshift and blue shift, these are both phenomena that work with any type of wave. A lot of people, when they learn about the Doppler effect in physics class in school, it's most likely going to be about sound, like the classic ambulance
Yes.
type of thing. Was that good? Misha, can we get a whoom?
There's an episode of The Big Bang Theory, which is like, maybe I've said this, I binge watched the day I failed my driver's license exam.
As you do.
And I never watched it again. It was just like I need something, anything. And there's an episode where Sheldon dresses up as the Doppler effect for Halloween.
How does he do that? Is it just like red on the top and blue or front and back? How is it?
No, he dresses in black, and it's like, I think it's like sound waves. Like, how when we record, we see the like bars going?
Yeah.
So it's kind of like that, where it's like quiet on the sides and like loud in the middle.
Oh, okay.
If I remember correctly, this is a long time ago.
Well, there's a lot of potential for error propagation here, because you might be remembering it correctly, but they could have just messed it up.
But they did it wrong.
The show,
Totally.
that show had its great things about it, but not
a lot of quirks.
It wasn't all gems. Yeah. Mm-hmm. But because a lot of people hear about the Doppler effect for the first time with regards to sound, they don't necessarily realize that it can also be applied to light. And that's true. The Doppler effect works with, well, I'll say like redshift in general, and we're going to get into the different types of redshift in this episode, because there are 3 different types of redshift that we're going to talk about. But in general, this phenomena works with all types of waves. Sound waves, which are pressure waves that travel through a pressurized medium like our atmosphere. Light waves, which we know from the electromagnetic spectrum episode, that can just travel through the empty vacuum of space. But also gravity waves, which travel through the fabric of space-time in our entire universe. And we talked about that a little bit, I think, in the black hole episode. Mm-hmm. But we are going to start with the most common type of redshift, and that's going to be from this Doppler effect that people have heard of. This effect was, I guess, it feels weird to say discovered, because I'm sure a lot of people before this dude had heard something with sound moving by them, and they realized that the pitch of the sound changes, or the frequency of the sound waves changes. But he was the first person to put it in a paper that we have. So his name was Christian Andreas Doppler. He's an Austrian mathematician / physicist / astronomer. He wore many hats. And he was born in the very early 1800s. Over his career, he published more than 50 papers about different things in physics and astronomy, but one of them, published in the original German, because he was Austrian, was called Über das farbige Licht der Doppelsterne.
What?
I
heard Uber.
I'm just flexing my German pronunciation skills, because everything else that I pronounce in this show is so wrong.
I saw it coming up in the outline, and I was like, I wonder if she's going to say this or not.
Yes, I am.
And
yes,
she
I am. So again, for the people in the back, Über das farbige Licht der Doppelsterne was a paper by Christian Doppler, published in 1842. And the English translation to that is concerning or on the colored light of double or binary stars. So this dude was looking at binary star systems, these pairs of stars that orbit each other, and he was studying how their color changes as they orbit each other, which they do, because as they orbit each other, each star is going to move like towards us and away from us as they're making the orbit. So the idea behind this Doppler effect that Christian Doppler proposed in this paper was that if you observe an apparent color change as the stars move with respect to us, then you can link that to the frequency of the stars and their motion, the velocity of their motion. So because the color that we perceive is a consequence of the frequency or wavelength of light, like 500 nanometers, we're going to see that as green light. Mm-hmm. Because there's that relationship, a star's change in color is related to its change in light frequency, or the apparent change in light frequency. And binary stars, as they're doing this dance, moving towards and away from us, we will see this change in color or frequency. But Doppler was wrong in some ways. Like, this effect is fantastic, but he incorrectly assumed that all stars are either white or yellow in color. And we know from the Stellar Types episode that that's just not true.
But that is how I drew all my pictures in school.
Right.
It's like, stars are yellow, and that's it.
You were drawing the sun.
Yeah, exactly.
Mm-hmm. The sun, our most famous star.
The most famous star.
So Doppler made that incorrect assumption. So many scientists throughout history have made incorrect assumptions, but they still contributed to our knowledge as a whole. And 5 years after Doppler published this paper, a French physicist named Hippolyte Fizeau,
perfect,
probably, confirmed the effect and added that it would be more useful to observe this Doppler effect by studying the star's spectral lines instead of studying the color. Because the spectral lines, it's more precise if you study those, because we have very precise measurements of where these lines, these spectral lines should be. And if the star is moving towards or away from us, then those spectral lines also shift.
Okay. And these are not the spectral lines that like the colorful spectrum that tells us like what it's made of. Is it the same?
It is
okay,
that same spectral lines, yeah. So when you look at that type of spectrum that shows you the absorption and emission features of a star or a galaxy or whatever you're observing, those emission and absorption lines should be at very specific wavelengths. So like if you have a molecular hydrogen line, for example, an H2 line, that should be at 21 centimeters. We have measured this in labs, we've measured this out in space, we know where that line should be. But if the object that is emitting that molecular hydrogen is moving, if it's coming towards us, if it's blue shifted, or if it's moving away from us, i.e. red shifted, then those spectral features will also move.
Oh, okay.
And we can measure how much those features have moved from their baseline point to get a sense of how fast that object is moving.
I think I got it. I'm familiar with like the spectrum lines from Space Center days, so it's really helpful to picture that. And I will make a note to share one of those on our Instagram.
Yes, please do. So even though Doppler got that a little bit wrong, it still stands that the observed frequency of an object and the actual frequency that it is emitting with and the speed of that object, all of those things are related. So if you know two of them, you can solve for the third. If you know the observed frequency and the actual emitting frequency, you can solve for the velocity. If you know the velocity and the observed frequency, you can solve for the actual emitted frequency. They're all connected like that. And you can just do some fun algebra to rearrange the equation. Now we're getting to the point where this is why I want to be at the batting cages today to record this episode. So red shifting with the Doppler effect means that an object is moving further away from you. Blue shifting means that the object is coming closer. But please remember that this is only an apparent shift in the star's color or frequency or spectrum. The inherent quality of the star is not changing. It's just kind of like an illusion as the star is moving. So this is how I like to think of it. Instead of picturing a star giving off photons, picture the pitching machine at the batting cage.
Okay.
Pitching machines, by the way, invented in California by a man named Lorenzo Ponza in the 1950s.
Cool. Sounds Italian.
So picture the pitching machine, and the machine is pitching out balls at a set rate, and it throws one ball every 5 seconds.
Okay.
The pitching machine is always going to throw one ball every 5 seconds, but if that pitching machine were moving towards us,
ooh, yeah,
it would seem like the balls are coming to us faster or closer together because they essentially have to travel less distance to get to us. Even though the rate of pitching hasn't changed, our rate of receiving the balls has changed.
Okay.
And the opposite is true too. If the pitching machine is moving away from us, then the balls have to travel further. And instead of getting a ball every 5 seconds, we're then getting a ball like every 10 seconds as the machine moves away.
Okay.
So that's redshift and blue shift right there. The stars are always emitting photons at the same rate, but if the star is moving away from us, then we're going to feel like we're getting photons more slowly.
Sure.
Yeah, that's the Doppler effect, and we can use it in so many areas of science to learn some really cool shit. So I looked up some examples outside of astronomy. One of them is radar, which is apparently an acronym for radio detection and ranging. Essentially, you have this transmitter that will send out waves, most likely light waves or like electromagnetic waves, but sometimes also sound waves, I guess. I don't know. I'm not a radar technician. And because the radar machine knows how quickly it is sending out those signals, when the waves hit something and get bounced back, we can determine if that object that it hit was stationary or moving towards or away from us based on the waves that the radar machine receives in return.
Sure, yeah.
Yeah, so that's radar. We can also use the Doppler effect for medical imaging. I saw a paper that talks about how it's used in echocardiogram, so imaging your heart and how healthy your heart is and how it is pumping blood around your body, because that's what hearts do, and that is the extent of my knowledge on hearts.
I do feel like an expert in like medical knowledge now because I started rewatching some of House.
Nice.
And I was like, oh yeah, I get it.
I haven't watched House in so long.
No, it was like a high school show for me. But I do hear the House theme song a lot. It's like always at a coffee shop, the House theme song is playing.
Yeah, Mass Effect, I think,
Yes.
is the band. Because it's an actual song. Mm-hmm. They didn't get it for the show. So you can be out in the wild and all of a sudden hear the House theme song. And you're like, oh, am I about to see some bad prognosis?
Yeah, the next time you hear the House theme song, tweet at Pale Blue Pod and let us know.
Please do. We want to know the rate.
Mm-hmm. And imagine the Doppler effect of the House theme song when you're closer and farther from it.
Yes. We will do this science, but you, listeners, you have to provide the data.
Yes.
Hi, it's Moiya here to give a shout out to our incredible patrons. Corinne and I really appreciate your support because, honestly, this show just wouldn't exist without it. So thank you, as always, to our sun-like stars, Sharn Llewellyn, Finn, Ian Williams, and Megan Moon. We love you all so much. Thank you for your support. And you, too, can support us. You can hear your name on this pod and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. Patrons get access to our research notes for every single episode with extra resources about each week's topic. The first 50 patrons will all be eligible to receive a free, signed, and personalized copy of my book, The Milky Way, an autobiography of our galaxy. And we are so close to 50. So please consider joining our Patreon or sending its link to your friends who just have like too much money and are looking for a podcast to throw their money at. So you can find our star chart and our Patreon info and more at our website, palebluepod.com, or just go right to patreon.com/palebluepod. We would love you forever. Thank you.
Do you want to learn more about science, math, AI technology? Just go to Brilliant.org. Whatever level you're at, Brilliant will help you master the skills you need. Brilliant is the best way to learn things like math and computer science interactively. There are thousands of lessons from foundational and advanced math to AI, data science, and more. And new lessons are added monthly. Even as a copywriter, I really need to know the ways to stay ahead as this industry is affected by things like AI. The skills I learned to build my career aren't exactly the ones I need now. And this is where Brilliant.org comes in. I'm a big believer in hands-on learning. I know that's how my brain works best, and Brilliant's visual, hands-on approach is such an effective way to master the key concepts behind today's technology. Plus, it's perfect for busy people, with bite-sized lessons that break down important concepts into understandable parts, kind of like Pale Blue Pod. Try everything Brilliant has to offer for free for a full 30 days just by visiting brilliant.org/palebluepod, or click on the link in our description. The first 200 signups will also get 20% off Brilliant's annual premium subscription. Again, that's brilliant.org/palebluepod.
Do you play games? And do you have questions about your feelings? Well, if you answered yes to either of those questions, then I have a podcast recommendation for you. It is Games and Feelings, also from the Multitude Collective. Games and Feelings is an advice podcast about games. You can join Question Keeper Eric Silver and a revolving cast of guests as they answer your questions at the intersection of fun and humanity since, you gotta play games with other people. And we're talking every single type of game here. Video games, tabletop games, party games, laser tag, escape rooms, game streams, D&D podcast, all of it. And the games themselves and the companies that make those games and the players that play them. They also have Jasper Cartwright, actor, D&D player, and host of 3 Black Halflings, as a permanent guest. I don't exactly know what a permanent guest means and how it's different from hosting, but that is what Jasper Cartwright is. So Eric, Jasper, and various multitude folks are recommending games, answering advice questions, and playing whatever quizzes Eric comes up with. And because this is a weekly show, they also have What's Your Favorite Pokemon? And then I Say Something Nice About You, where Eric interviews people about their favorite Pokemon and then says something nice about them. Isn't it awesome when something's name tells you exactly what to expect? So if you like what you hear about this Games and Feelings podcast and you want to level up your emotional intelligence stat, subscribe now wherever you get your podcasts. New episodes are out every Friday. Just search for Games and Feelings in your favorite podcatcher. And, of course, the use of the Doppler effect that is nearest and dearest to my heart is that we can use the Doppler shift to study the radial velocities of stars that have planets orbiting around them. Radial velocity means how fast are you moving towards or away from us. So it's specifically in that direction. There's a different type of velocity for motion to the left and right and motion up and down.
Oh, okay.
So with the radial velocity method, this is like the second most successful method of finding exoplanets out there. And we're going to do a whole episode about exoplanet detection methods, so I'm not going to get too into it. But as the planet orbits around the star, it actually tugs on the star a little bit and makes the star wobble or orbit a tiny little bit around the center of mass of the whole system. And as the star is wobbling, it will move towards and away from us. Its spectrum that we are studying will shift, blue shifting and red shifting, and we can measure how much the spectral features have been shifted to study how fast the star is moving. And that stellar velocity is going to be directly related to the mass of the planet that is tugging the star.
Cool.
Which is how we determine the masses of exoplanets. It's amazing. There are such indirect methods, and I love it. That's the Doppler effect, red shifting from the Doppler effect. But I said there are 3 types of redshift, so we still have more to learn. Any thoughts or questions on that bit?
I have one question, and you tell me if this question means I don't understand. When it says closer and further to us, is it relative to like where we are on Earth or just general to planet Earth? Like if I'm in the southern hemisphere, is there any difference?
No. The size of Earth is so much smaller than the distances to these objects that it doesn't really make a difference.
That makes sense. Well, that's
So
cute.
I think you do understand it.
I do get it.
Yeah, you're learning. That's so exciting. The next type of redshift that I want to cover is gravitational redshift, which means we're going to have to go back to Einstein and his theory of general relativity because it just keeps coming up, which I guess is what happens when one guy discovers how gravity works and we live in a universe where like almost everything is
about that.
Is about gravity, yeah. So we're going back to general relativity. Einstein, in his theory of general relativity, not special relativity, predicted that light or photons, remember light is both a particle and a wave, so photon particles and light waves can be redshifted as they move away from a very massive object. The language that I saw a lot when I was researching this, and some language that you might have heard in the past, is as the light is climbing out of a gravity well, it will get redshifted.
Wow.
Because we often talk about big, strong gravitational fields as wells, as pits that things can fall into.
Yeah, scary.
So we can also think about things climbing out of those pits if we can think about things falling in.
All I'm picturing right now is The Ring, is the movie The Ring,
Oh,
and the
no.
well. The well in the ring. But I'm trying to, but in that movie is very dark. And in this scenario, we are discussing light. So maybe that's soothing.
What's the opposite of a ring? Like what would be the opposite of this movie? What would be the light version of the ring?
Monsters, Inc. I'm just picturing movies I love that are nice.
Monsters, Inc.
Elf.
Yes. Well, if the person from the ring was crawling out of a deep enough gravity well and also happened to be a photon, then she would get redshifted as she climbs out.
That would be amazing for her.
Yeah, good for her. getting redshifted. Actually, I don't know if that's a good thing in the context of like the human experience.
So true. But she's already bad news.
Yeah, so it can't get much worse,
Can't
right?
get worse
There's
for her.
only up from there.
I'm going to not like her no matter what, so I don't really care.
I have never seen this movie. I don't plan on ever watching this movie, so...
I don't recommend.
Okay, good to know.
Too
Thank
scary.
you. Thank you, Corinne.
Too spooky.
I'm a little wuss. The universe does not scare me, but horror movies absolutely do.
Yes, too scary.
Too scary. Gotta watch with the fingies deployed.
Yes.
And the fingies are like when you take your hands and you split your fingers down the middle.
Star Trek
so you
style.
are still watching. Yeah, Star Trek style. So you're still watching, but you can very quickly close the shutters, you know?
Exactly.
Okay. So let's explain this gravitational well thing. It takes a lot of energy to escape a strong gravitational pull or to climb out of a gravity well. But the thing about photons is that they're always going to travel at the speed of light in a vacuum. Like in the vacuum of space, they're going to travel at 3 times 10 to the 8 meters per second. That is their speed, and that doesn't change. But that's like the most effective way to absorb or release energy is to change your velocity. So photons have to do something different in order to maintain the amount of energy in the system, because another rule of physics is that energy cannot be created or destroyed. It has to go somewhere. Mm-hmm. So when these photons are trying to climb out of a strong gravity well, the only way that they can save or like trade their energy instead of going slower, they have to shift their frequency to one with less energy. So a photon that typically would have a wavelength of, I'm going to use 500 nanometers again, a green light photon, if it were escaping a gravity well, it can't move slower. Instead, it has to go down to a lower frequency, which is a longer wavelength, and it now has a wavelength of like 700 nanometers, which is red. Mm-hmm. So these photons are essentially getting redshifted.
Got it.
We can see this. We've seen this in practice. We've seen this in labs. We have seen this out in space around neutron stars. But neutron stars, even though they are the second densest objects in the universe after black holes, they will only produce the tiniest shifts. One person who did the math that I didn't want to do, the result was that it's less than 1 part in 30,000. Like, that's how minute.
That's tiny.
These shifts are, yes. In my notes, I wrote tiny and I put like 10 eyes. That's how small it is.
Tiny.
But the reverse is also true. So if a photon is falling into a gravity well, and we see this with black holes that are attracting stuff all the time, well, then you're picking up energy from the system, but you can't move faster as a photon. So instead, you have to shift your frequency to one with more energy. So it's kind of like, imagine you're bungee jumping, right? Mm-hmm. And normally, as a human, when you jump, you would succumb to the acceleration of gravity. You would fall at a rate of almost 10 meters per second, and you would get faster as you get closer to the ground. But if you are bungee jumping as a photon, you're already going as fast as you can go. So you can't speed up, you can't increase your velocity, but that kinetic energy has to go somewhere. So it's almost like the photon absorbs the kinetic energy, and you can use that through glowing or like screaming or something. I don't know. But this is how gravitational redshifting and blue shifting both work. We have definitely observed gravitational redshifting out in space. Honestly, I didn't look for examples or evidence of gravitational blue shifting because like we know stuff is falling into these black holes. Like we don't really have to.
If we listen carefully enough, we'll hear them scream.
we'll hear the photons scream as they bungee jump into a black hole.
It's a happy yelp.
Yeah, you're right. I think I just really want to go bungee jumping soon.
Oh my gosh. Have you ever gone?
No, but I am kind of a thrill seeker. Have you? Would you?
I think I probably would. I don't know. Maybe.
Would you go if you were a photon and you knew you wouldn't go fast? Or at least not faster than you're used to going?
Probably yes. Maybe. Well, but in that scenario, it's a black hole.
Yeah.
And we did soothe a lot of my fears of them.
Good.
But I don't know if I like thrills. I get my thrills from watching The Ring, and that's it.
You and I have such different methods of getting our adrenaline pumping. So we will not be doing a pale blue pod bungee jumping trip is what I'm hearing.
I'll meet you at the bottom for a drink.
Okay. And then you can watch The Ring while I drink that drink and look away.
Exactly. And that would be a great day.
Of course. All right, so that is gravitational redshift. Now we're moving on to cosmic redshift, or like cosmological redshift, it's sometimes called. And this is, I think, my favorite redshift. It's not why I saved it for last. I saved it for last because it's like redshift on the biggest scales, but I also think that it's really interesting because it teaches us about the expansion of the universe.
Cool.
Edwin Hubble, back in 1929, was responsible for finding evidence that the universe was expanding instead of sitting in this static, non-moving state, which is what people like Einstein thought the universe was doing. So, like, fuck you, Einstein. That's what Edwin Hubble would say, I'm sure.
His words, not mine.
Not mine. Look, I'm just the messenger. Don't shoot me. So it's 1929. Edwin Hubble is like kind of fresh out of grad school. He has attended the great debate talking about whether or not there are other galaxies in the universe. And now he is studying those other galaxies to see how they are moving. And what he finds is that those galaxies are moving away from us. But there are two important facts here that tell us that this redshift is not the same as the Doppler effect. Because that's an easy assumption to make. Oh, those galaxies, they look red, they're moving away from us. It could very well be the Doppler effect. But no, it's not. And we know that for a couple reasons. One, the galaxies that are farther away from us are moving away from us more quickly.
Okay.
Does that make sense? Yeah. So a galaxy that is 10 kiloparsecs away from us is moving faster than a galaxy 5 kiloparsecs away from us. And you don't have to know what a kiloparsec is. That's just a unit of distance. You know that 10 is bigger than 5, so that's fine.
Yes.
So if this were due to the Doppler effect, then there wouldn't be that coherent trend. Galaxies closer to us could move faster than galaxies more distant, but instead we see this very strong correlation. It's a line. We fit a line to this. The galaxies that are further away move faster, which tells us it's probably not the Doppler effect. But there's also something else that tells us that. These galaxies, where we see this effect in all directions. So no matter where we point our telescopes, we see that more distant galaxies are moving away from us at faster speeds. And you could take a very simple read on this situation and say, oh, well, all the galaxies, they're moving away from us because we're the central point in some big universal explosion. But really, that's so anthropocentric. Like, that's the highest level of humans are the center of the universe that you could possibly get to. And it's just not likely. It's much more likely, it makes a lot more sense for the entire universe to be expanding away from itself because we are not special. We really aren't.
It's true.
So a lot of people, when they hear about the expansion of the universe, a common balloon analogy comes to mind. And I think I've talked about this in previous episodes. But that balloon analogy is fantastic only if it's described well.
Okay.
So, like, people will put markings on a balloon and they'll blow it up, and people will think that it's the volume of the balloon that we're talking about, that it's like the space inside the balloon that represents the expanding universe. But that's not true. It is the surface of the balloon that represents the expanding universe.
Oh.
Because it's not that everything in the universe is moving away from stuff, it's that the space itself is stretching.
Oh.
So these galaxies that are moving away from us, that are redshifted, it's not that those galaxies are moving through the universe. They're trapped in the soup, and the soup itself is stretching.
Is ballooning.
Exactly.
Sure.
They're just sitting there and getting carried away.
That makes sense. That's a good way to think about it. I was telling Moiya I went to a child's birthday party this weekend, and I did blow up balloons, so it's close to home.
Yeah, you could have taught them about the universe expanding.
Yeah, I was just trying to get him to not eat it, because he's one. So, next birthday.
Next time. 2 years old is the right time to learn about the expanding universe.
Exactly.
Other things about cosmological redshift. So we can measure this We can measure how much cosmic redshift a galaxy or some other target is experiencing. And then we can work backwards to figure out how far away that object must be. The unit for redshift that we use, or like the variable that we use to denote redshift, is a Z, a big Z. Confusingly, Z is also the variable that we use to denote a star's or a galaxy's metallicity. Do you remember about metallicity, Corinne?
I remember the word, and I remember being like, I've never heard that word before.
It's a weird word. It is the fraction of elements in a star or galaxy that are heavier than helium, because astronomers call anything heavier than helium a metal. And both metallicity and cosmic redshift are denoted with the letter Z because we suck.
Because they want to make it hard.
Exactly. But this Z, this redshift, is a unitless parameter, meaning it doesn't have units of like time or length or mass or anything. It is a unitless number that we can use to figure out how far away something is. I really like talking about cosmological redshift because I've studied what I thought were distant galaxies. I once studied a galaxy that was 250 million light years away from us.
Whoa.
And that, for most people, like, that's a distant galaxy. It's well outside of our local group. But in terms of cosmology, for people who study the entire universe, that was nearby. And you know that it's nearby because its redshift number was like 0.01 or something, like 0.1.
Yeah.
Like, it was so small.
So low.
We see galaxies that have redshifts of like 12.
Wow.
Those galaxies with high redshifts would be billions of light years away. Like, when we observe a galaxy with redshift 12, we're looking at a galaxy as it was less than 1 billion years after the Big Bang. It's amazing. So I really like redshift.
That's cool.
But I love it because astronomers now understand cosmological redshift well enough to use it to determine distances to these most distant objects, these most faraway objects. In fact, cosmic redshift is the final rung on what astronomers call the distance ladder. Have you ever heard the term distance ladder?
No.
Yeah, why would you?
No, but I like it.
I devote almost an entire chapter of my Milky Way book to the distance ladder because I think it's so valuable to understand astronomy, and we should absolutely do an episode about this in the future. But
yeah,
the distance ladder itself is a sequence of methods that astronomers use to determine astronomical distances. There are several rungs on this ladder that are each useful for more and more distant objects. So like the first rung on the ladder is something called parallax, which we will get to in that episode on the distance ladder. But that method only works for very nearby objects that are like definitely within our local group, most likely within our galaxy. To measure distances to more distant objects, you have to work your way up the distance ladder, and cosmological redshift is used for the most distant objects. It is the final rung on this ladder.
Cool.
Which I just think is fun because of that relationship between the distance to an object and the velocity with which it moves away from us.
Yeah.
Any questions about cosmological redshift?
So, for cosmological redshift, is the color involved as much?
Yeah, yes. Oh, thank you. That's a really good question. So in the Doppler effect, redshift with the Doppler effect, the wavelength of light is not actually changing. It's just that because the object is moving farther away from you, it's taking that light longer to reach you. So it feels like the wavelength has shifted. With cosmological redshift, as the fabric of space-time gets stretched, so do the wavelengths of light. Yeah, so do the light waves in the fabric of space-time. So like these light waves actually are getting shifted towards the red, it's just the red. There is no cosmological blue shift.
Cosmological blue shift. Sounds cool.
I mean, and we'll also do an episode on this, but one potential scenario for the end of the universe is called the Big Crunch. And in that scenario, the universe expands until whatever is fueling that expansion loses out to gravity because of all of the matter in the universe. And so the expansion stops, and then it rebounds on itself, and it comes back together. And I guess in that case, there would be cosmological blue shift because the universe would be, like the fabric of space-time would be contracting, and so would the light waves.
Would it be, when I hear crunch, I think of something very quick? Would it be like a quick contraction or in this theory, or would it be like slow?
It would be about as slow as the expansion of the universe has been. It would speed up as stuff got closer together. Mm-hmm. It's called the Big Crunch because at the end, you know how, according to the Big Bang Theory, everything in the universe was once contained in a tiny little primordial atom. Mm-hmm. We call this scenario the Big Crunch because eventually everything would crunch back into that primordial atom.
Ooh.
Yeah.
That makes me hungry.
I do kind of want a crunch bar now.
I love crunching.
Not to be confused with crunches.
No.
Which is the opposite of eating a crunch bar.
Which I don't like.
No. Also, they're not that effective. There are other better exercises.
Exactly.
Yeah, they just hurt your back.
Yes, they're not comfortable to do. And like standing core work is like more satisfying for me.
Yeah.
And I have tight hip flexors, so crunches aren't for me. But a big crunch.
Big crunch is for everyone.
But I would do a big crunch.
Things you never expect to hear on an astronomy podcast. The efficacy of crunches versus other deep core exercises.
Yeah. The big plank.
Do some weighted marches.
Yeah, some oblique
dead
stuff.
bugs. Yeah,
Yes.
like you got it. Yeah, that's all I have to say on the 3 types of redshift. Do you have a favorite type of redshift?
I'm really into this cosmic redshift too.
Yeah, it's great.
I really like it, and I think it's just, I think that's such a fun, mysterious part of the universe to me is like the expansion, and I think I'm always going to kind of like the stuff that contributes to our knowledge about it.
Yeah, I agree. Okay, so my friend Sean is a comedian writer who I am developing a TV show with. So, like, hopefully that
Hell yeah.
becomes a thing. But Sean is very funny. And one time I was talking to Sean about my dating life, and the topic of ghosting came up. Mm-hmm. And he was like, oh, I've never really ghosted anyone, but I have just, like, slowly petered out my communication with someone so that eventually they got the hint. You start off texting every day, and then it's, like, every 3 days, and then it's once a week. And I was like, oh, Sean, you redshifted them.
Yes, that's good.
It's good, right? Because you're essentially weaning someone off of your presence. Mm-hmm. But it is very similar to a galaxy that's just like moving further away. And it feels like they are communicating with you less and less. It feels like the wavelength is growing.
That's really fun.
Is there any other definition that you can think of for redshifting? Any other scenario where that might be useful?
Redshifting really makes me think of, like, personality change.
Ooh.
And maybe that's too dramatic, but...
Let's go for it.
A redshift or a blue shift personality change? I mean, I'm so in my head about politics right now, so I'm really thinking of, like, the political spectrum, which is maybe not it.
I thought you were going to go like anger versus peace, if someone is in anger management therapy, they're being blue shifted.
Exactly. I think of blue, maybe this is funny about me, but I think of blue as a very calm, peaceful emotion, and red as like a lot of energy and a lot of anger. And I guess
Even
in
though
that
it's
way
totally
they're
opposite in science. Yeah.
Well, what am I thinking of right now? That Pixar movie, Inside Out. Not to just mention Pixar so many times.
Oh yeah.
But blue was the like sad character, and red is like the little angry guy. Mm-hmm. And I can really relate to both of them.
We all contain each of them within us.
Exactly.
All right. Well, I hope that you are not out there getting redshifted in the romantic or platonic setting. But I do believe, unfortunately, Corinne, I signed us up for slots in the batting cages just to see how we do.
Oh,
and
my gosh.
it's almost our time, so we should get going.
What if I'm amazing?
I think you will be. I believe it.
I think you're going to get better by the end of this session.
Well, the jury's still out on me, but I'm here to watch you shine like a baseball star.
I'm going to get a half home run.
And no matter how many fractions of a home run you are hitting tonight, remember, you are space.
Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.